The remarkable twin Voyagers have become part of our collective admiration and awe for what they accomplished, and all since the 1970s. Let's take a look at these remarkable spacecraft and find out why Voyager 2 launched first, and why Voyager 1 traveled faster than Voyager 2, and how did the Voyagers work. In the beginning, there were actually 3 Voyagers built. VGR 77-1 was called Proof Test Model and was used for testing and was put through some very rigorous tests. The other 2 craft, called VGR 77-2, later called Voyager 1, and VGR 77-3, later called Voyager 2, were tested also, but not so rigorously, because they wanted to preserve them for launch instead. Voyager 1 developed failures in its attitude and control system during its testing. It was planned to be launched first on August 20th, but its launch was postponed because of the problem, so Voyager 2 was launched instead. Since Voyager 1 and Voyager 2 had different planet explorations planned, Voyager 1 launched on September 5th on a different, faster trajectory, resulting in its arrival at Jupiter 4 months ahead of Voyager 2. They each weighed almost a ton and included a 12-foot diameter radio dish to communicate with Earth. Each spacecraft was built with 16 hydrazine thrusters, 3 gyroscopes, gimbals, 8 backup thrusters, 3 radioisotope thermoelectric generators, 11 science instruments, and a myriad of their subsystems, and 3 dual redundant computer systems. And each spacecraft was comprised of 65,000 individual parts. The electronics were housed in what is called the bus. This is the black 10-sided box below the antenna. It measures 7 feet across and 24 inches deep. Each of the 10 sides was associated with a compartment or bay, which is where all the computers, electronics, and their subsystems, including engineering systems, data storage, flight data, telemetry, attitude and articulation control, radio communications, heating controls, and the power supply subsystems were located. Components were rack-mounted for installation in the bays. The center line of the bus is called the Z-axis. There was also the X-axis and the Y-axis. The spacecraft was designed to roll on these axes by firing small thrusters, which fired tiny millisecond pulses. There were 8 sets of thrusters altogether, placed around the spacecraft, along with their backups. These thrusters were used to rotate Voyager around all 3 of its axes at a rate of 0.3 degrees per second, keeping the antenna pointed at the Earth. In the center of the bus was located a spherical propellant tank that contained 231 pounds of hydrazine, which fueled the thrusters for attitude control, trajectory corrections, some power applications, and also fed heater lines to keep components warm. If attitude and control or ground stations on the Earth detected that the antenna was not pointed in the right direction, a signal was sent to Voyager's computers, which in turn activated the appropriate thruster that would gently nudge the antenna into the right position. In addition to the attitude control thrusters, there were 4 sets of thrusters called trajectory correction maneuver thrusters, allowing NASA to finely control the craft's trajectory over time. Connected to the framework of the bus is the antenna, and extending away from the bus are 3 booms, a science boom and scan platform, to which most of the instruments are mounted, the magnetometer boom, and a boom to which the RTG power generators were mounted. Because of the further and further distance from the Earth and the time lag for communicating, the Voyagers were designed to operate mostly autonomously. Each craft had 7 top-level fault protection routines, each capable of covering a multitude of possible failures. The spacecraft could place itself in a safe mode in a matter of seconds. The computer systems were also built to be self-repairing. 3 computer systems inside the bus were the heart of operations. The bus contained 2 command and control computers, 2 flight data system computers, and 2 attitude articulation control computer systems. Each had a duplicate unit for backup in case one failed. That's why there were actually 2 of every unit. In addition to the computers, the bus bays held a myriad of systems and subsystems controlling every aspect of the spacecraft. The bus bays were numbered 1 through 10. Here is a diagram of the bus bays and the corresponding equipment located in each. The computer command subsystem was located in Bay 3. Voyager was the first to use a computer to be able to detect and solve its own problems. The CCS was the heart and soul of Voyager. It was the central controller of the spacecraft. The CCS was responsible for managing overall operations, including program sequencing, communicating with other computers, and uploading programs to memory. Each of the CCS computers had 69.63 kilobytes of memory total. That's about enough to store one average Internet JPEG file. The computers were capable of executing about 81,000 instructions per second. Voyager's computer software was originally written in assembly and Fortran 5, but later ported to Fortran 77. The Voyagers did not have an operating system. The CCS had 2 of everything: power supplies, processors, buffers, inputs, and outputs. Each element of the CCS was cross-strapped, which provided redundancy so that if one part failed, it could make use of the corresponding remaining operational part in the backup unit. Each of the 2 CCS computers could operate individually, in parallel, or in tandem with each other. The CCS was programmable while in flight. Although there was no actual clock, the CCS could count hours, minutes, or seconds until some pre-programmed interval had elapsed, and allowed the CCS to branch into routines stored in memory, resulting in commands to other systems. Voyager control systems could record sets of several thousand instructions, allowing autonomous operation for days or weeks at a time. The Attitude and Articulation Control subsystem in Bay 5 provided attitude and orientation control so that the spacecraft's antenna was always pointed toward the Earth. Actually, with the aid of a sun sensor, it kept a lock on our sun, a fixed point from which it could track where the Earth would be in its orbit around the sun. It could then calculate exactly where to send the signal. The AACS, by using the craft's thrusters, could position the Voyager, rotating the craft along its axis. The AACS kept track of the health of the Voyagers and sent a report of the craft's health to the CCS at regular intervals. The AACS also controlled motion of the scan platform upon which the remote sensing instruments were mounted. The AACS decided what the elements of the Voyager needed to do, then sent that information to the CCS, and the CCS issued commands to the appropriate unit to take the appropriate action. The Voyagers were the first to use a computer to control attitude and articulation. The sun sensor was attached to and looked through a slot in the antenna. It kept track of where our sun was in relation to Voyager. It detected the sun as the brightest object in space and commanded Voyager to rotate until it locked onto the sun. This correctly aligned the X and Y axis. A gyroscope and gimbal aided in the alignment process. If it detected a position error, it sent a signal to HiPACE, a computer in the attitude and control system, which then signaled the appropriate thruster to fire. Also attached to the upper ring of the bus were 2 Canopus Star Tracker units. It was called Canopus Star Tracker because the unit would lock onto the star Canopus, brightest in the night sky and located above the south ecliptic plane. It would also notify the HiPACE system, which would in turn instruct the spacecraft to roll about its z-axis until it locked onto Canopus. Voyager's orientation to the Earth could be adjusted manually, but it was also programmed to autonomously reset its antenna orientation multiple times a year to ensure a stable connection with the Earth. Next, in Bay 7, is the Flight Data Subsystem. This is where all engineering and science data and telemetry was collected, formatted, and prepared for transmission to Earth. If a high data rate or contact with antennas on Earth could not be established, then data was stored for later transmission. Data storage capacity was the equivalent of 100 full-resolution photos. The FDS, like the CCS, was programmable while in flight. Next in Bus Bay 2 was the digital tape recorder, which was used to store data when real-time communications with Earth were either not possible or not scheduled. The DTR recorded data on an 8-track tape unit. This was not your grandfather's 8-track tape player. This one used a metal tape, which was specially designed to withstand the rigors of space travel and had a more sophisticated operation. The capacity of each track was about 0.5 gigabyte. The DTR on Voyager 1 was shut down for good in 2007, not because of any issues with the unit, but because of the dwindling power supply coming from the craft's RTG generators. The digital tape recorder on Voyager 2 was still functioning, but would be shut down due to dwindling power supply. In Bay 7 are the heater controls, which were responsible for keeping Voyager warm against the brutal cold of outer space. The power regulation electronics located in Bay 7 helped regulate temperature of the propellant lines from the hydrazine tanks to the thrusters, as well as heat for the other components. Electric heaters were located throughout the spacecraft, but heaters were turned off in those bays where valves, instruments, or subassemblies were on and producing their own heat. In addition to heaters, both the top and bottom of the bus were wrapped with black, multi-layered thermal blankets to protect Voyager from rapid loss of heat to space. The blankets were sandwich layers of aluminized mylar, sheets of Teflon for micrometeoroid protection, and black Kaptan covers that were electrically conductive to prevent accumulation of electrostatic charges. Smaller blankets and thermal wrap covered 8 electronic bays, boom and body-mounted instruments, cabling, hydrazine lines, which become solid at 36 degrees Fahrenheit, and structural struts. Only a few exterior elements were not covered. Temperature controls of 4 of the 10 bus bays were also provided by thermostatically controlled louvers, providing internal near-room temperature in those areas. Louvers were placed outside of bays 1, 2, 7, and 5. The magnetometer boom is a marvel of engineering. The magnetometer boom is located on the opposite side of the spacecraft from the science boom. One low-field magnetometer was placed 23 feet along the boom, and the other at the end of the 43-foot boom. This was done to keep them away from interference from onboard electronics in the bus. The boom is also known as an astromast. It is triangular in shape and made of fiberglass. 3 long rods run the length of the boom, and it is held together by fiberglass trusses, diagonal filament struts, and fastened with flexible joints. The entire boom is collapsed by twisting it and laying it in coils into a small 2-foot-long canister. The Voyager's boom canister was only 27 inches long, yet held a 43-foot boom when extended. It was in this collapsed position during launch. After launch, General Pyrotechnics deployed by the Pyrotechnic subsystem released the latches holding it in place, allowing the boom to slowly extend under the spring force of its twisted fiberglass rods. Pyrotechnics were used on all 3 booms to release levers holding each. This is how the magnetometer boom was deployed. During Voyager's time in the solar system, the magnetometers were used to investigate the magnetic fields of the outer planets, their moons and rings, and their interactions with the solar wind and the sun's magnetic field. After leaving the solar system, they were used to explore the transition region of the solar wind boundary, where the sun's magnetic influence interacts with and gives way to the magnetic field of interstellar space. Information gathered by the magnetometers was sent to the Flight Data Subsystem for further transmission to Earth. The Science Instrument boom is located 180 degrees opposite the RTG boom, because the Science boom instruments were the most sensitive to radiation. The boom itself was made of rigid fiberglass and extended 13 feet from the body of the craft in order to keep the instruments away from any interference from electronics in the bus or radiation from the RTG. It was placed into a folded position for launch, but after launch, pyrotechnics released latches holding it in place and allowed the release of the boom, which then snapped into place. The flight data subsystem in Bay 4 controlled the science instruments and formatted all science and engineering data so it could be transmitted to Earth. Mounted on the boom first is the plasma detector, which looked for the lowest energy particles in plasma. It looked for their speed and direction from which they came. It also studied the solar wind and helped detect and study the boundary between our solar system and interstellar space. This was particularly useful in determining when Voyager entered interstellar space. Next is the cosmic ray detector, which had the highest sensitivity of Voyager's sensors. It detected the abundance of particles from inside the bubble of our sun's influence, particles that dominate outside of the bubble in interstellar space, as well as look for very high energy particles from the sun and galactic sources. These readings also helped determine when Voyager entered interstellar space. The low-energy charged particle detector and its 3 sets of particle sensors measured how many low-energy particles hit it and determined the speed of those particles. It was used to study cosmic radiation and particles and the difference between those particles that emanate from the sun, the planets, and interstellar space. It had the broadest energy range of the 3 sets of particle sensors. This was also particularly useful in determining when Voyager entered interstellar space. The plasma wave subsystem used 2 long antennas on the spacecraft, which stretched at right angles to one another. This was used to measure the electrical field components of plasma waves at the outer planets, but later, the instrument provided information about the changes to plasma waves as Voyager entered interstellar space. And at the end of the science instrument boom was the scan platform, which included 4 instruments. The AACS could move this part of the boom independently from the rest of the craft, manipulating and turning its instruments toward positions of interest, maximizing their ability to collect their information. The scan platform could point its science instruments to an accuracy of 1/10 of a degree. Located on the scan platform was the Imaging Science Subsystem, consisting of 2 black and white television-type cameras, one with low-resolution wide-angle lens, and the other a high-resolution narrow-angle lens, which was sharp enough to read a newspaper headline at a distance of 0.62 miles. Voyager 2's cameras were shut off in 1989, and Voyager 1's camera was shut off in 1990 after taking a picture of the famous pale blue dot. Shutting off the cameras would not only save power, but after leaving the solar system, Voyager would not come anywhere near another astrological body for 40,000 years. Next was a photopolarimeter, which was a small telescope with polarizing filters and which studied particles in the atmospheres of the outer planets by measuring the way light gets scattered as it hits the particles. It also searched for optical evidence of lightning and auroras. It had not been used since the 1980s, however, when the Voyagers left the solar system, because it had reached the limit of its range and because of the darkness of outer space, there was no more light available. Next was the infrared interferometric spectrometer, which studied what types of elements were present in the atmospheres of the outer planets, as well as their surfaces. It also measured the amount of sunlight they reflected. And last was the ultraviolet spectrometer, which was a specialized ultraviolet light meter. It identified particles present in planetary atmospheres by studying atomic absorption. Information gathered from each of these instruments was sent to the Flight Data Subsystem, located in Bus 4, where the data was collected, formatted, and stored for transmission to Earth. Voyager communicated with Earth via a 12-foot high-gain parabolic reflex antenna for sending and receiving communication with the Earth. All data was transmitted from and received by the dish antenna. In Bay 9 was the telecommunications subsystem electronics. These were the electronics associated with the duplicate pair of transponders, which did the actual sending of the signals to Earth. As with all the other equipment duplicated on Voyager, if one transponder failed, it could be bypassed by shifting to the duplicate unit. The TCS transmitted science and engineering data to the Earth. It also received instructions sent from Earth, which was then sent on to the computer command subsystem. The antenna reflector had an aluminum honeycomb core and was surfaced on both sides by graphite epoxy laminate skins. The antenna is connected to and supported by aluminum tubular trusswork above the bus. Information gathered by Voyager was converted to ones and zeros, then given to the telecommunications subsystem transponder that then placed those numbers onto radio waves. The information was then sent on those radio waves to Earth, where it was decoded. Voyager's main transmitter radiated about 20 watts. By the time Voyager's signal reached the Earth, its strength had diminished to about 20 billion times weaker than a digital watch battery. In 1978, the primary radio receiver on Voyager 2 failed, so the backup receiver was used ever since. Voyager was actually equipped with two antennas, a smaller low-gain microwave antenna and the larger high-gain parabolic dish antenna. The small low-gain microwave antenna went out of range during the 1980s and had not been activated since. The large 12-foot diameter parabolic dish was not folded for launch. Instead, the aluminum fairing cone was fit over the antenna for launch. Power was supplied by 3 radioisotope thermoelectric generators. They worked by converting the heat given off by the decay of radioactive plutonium-238 into electricity. When Voyager was launched, the 3 radioisotope thermoelectric generators converted 7,000 watts of heat into 475 watts of electrical power. Power was held constant at 30 volts DC. Power was either supplied to some of the spacecraft equipment directly or by command actuation, where power was switched to equipment in the power distribution assembly. RTG electrical output decreased about 4 watts per year because of the decay of the plutonium dioxide fissionable material and degradation of the silicon-germanium thermocouples, that part of the RTG that did the conversion of heat to electricity. Prior to launch, the RTG boom was folded into place so that the launch cone or fairing could be slipped over it. After launch, latches were activated to release the boom, allowing it to snap into place. Considering the decay factor of gold in outer space and its reaction to radiation, it is estimated that the gold-covered records attached to the Voyagers will last more than 1 billion years. On a per capita basis, the Voyager program cost each U.S. resident about 8 cents per year.